So for today, I prepared a little slide deck with a different title than we had originally planned, because originally we thought, let's discuss another API example, but a transactional this one. But for various reasons, I decided to give it a different twist this month, and talk a little bit about some core performance principles. Why? Because obviously I deal with performance a lot in my work, since I'm a member of the real world performance team. And we often are able to bring performance gains in orders of magnitude, and not just make something 20% faster, but make something 10 times or 100 times, and in extraordinary cases, even 3 orders of magnitudes faster. And very often this involves a move from something that's been built in a layered software architecture, where SQL is invisible to the developers, since all the SQL is being generated by frameworks, moving that to a SmartDB architecture where the SQL is handcrafted. That's when you get these orders of performance gain, and I'm sure others in the call or not in the call have had similar experiences. And I want to talk about the core performance principles that lay behind the fact that you can get these orders of magnitude speed up. So that's the agenda for today. I'll probably be talking 35 minutes, and then we can have some questions for the rest of the time that we would like to have questions. Now, before I move into the core performance principles, let me spend a minute or two on layered software architectures. Can anybody see the right bit here? Because
I can see the whole of the screen.
Okay, great, perfect. So the layered software architecture is a way of building applications that came into existence, I think, at the end of the 90s, early 2000s, where we talk about N-tier architectures. Java EE was the main driver for this type of architecture. It's been widely used by architects, designers, developers the past 20 years. And in these architectures, we see layers, major layers of software running on typically an application server, where we have the database layer on a database server, and then on an application server, a persistence, a model, a business, and a presentation layer. Those are the main layers that we typically see, and these layers are then supported by, or you design and develop your software architecture, your application code, using frameworks that map to these major layers. And I've just put up a subset of frameworks up here: ADF, Spring, Eclipse, Hibernate, JDBC. All these frameworks have their own sublayers, and some of these frameworks, they match just one layer on the right, or others, they have different frameworks in them matching towards multiple layers in these major layers architecture. And of course, there are many others. You've probably all seen these and are aware of them.
Toon, can
Yes.
I interrupt just to ask you to clarify the terminology here? We hear the word tier in use. In fact, you had N-tier on an earlier slide, and you're now using the word layer. What I've come to almost guess, read between the lines, is that tier refers to actual distinct machines, while layer refers to some more or less well-defined notion of subdivision of components within a single executing program. Is that how you see the terms?
That's exactly how I see it also, yeah.
Right.
So
and as far as it concerns the tiers, we in SmartDB land don't think it's in any way questionable to have a database tier and some kind of middle tier. Sounds silly when I say it that way. And browsers at the far end of it. We're happy with that, yes? Yes. Right, on you go.
And again, in these layered software architectures way of working and building your applications, all these layers typically live in a middle tier / application server, where all the code runs, and from which all the SQL is being generated and submitted towards the database tier that houses the database instance. Now, there's a reason why we started using these frameworks, obviously, because when you build an application, there's a lot of plumbing that needs to be taken care of. I'm not saying the word plumbing to give it a negative tone. You need to. There's a lot of work that's not interesting that frameworks can do for you as a developer. So these frameworks, they abstract away the uninteresting work. That's typically one of the reasons why these frameworks are being used. And the fact that this really happens is there's a nice screenshot here where we see a code stack dump with many layers inside a JVM, where there's only a tiny little bit that the developer actually has to code. And then there are many layers underneath that make sure that whatever is being changed here or whatever data needs to be visible here is being queried upwards from the database, or change data is being put backwards into the database. Yeah, so all the SQL is invisible, and again, going upwards towards the browser, how to generate HTML and deal with all kinds of HTTP events is all being taken care of by these layers. Supposedly, again, resulting in developer productivity. That's why we have seen such a big rise of these layered software architectures the past 20 years. Now, and I think I've talked about this a couple of months ago in one of our earlier office hours, is these layered software architectures, they imply that since all the SQL is generated, you get this row by row SQL, primitive use of SQL towards the database, which in turn implies you get this chatty behavior towards the database. But there's also a third really important thing, and I'm calling it here long reservation times of connections from the connection pool, and I'll come back to that in 10 minutes. But let's first take a look at these two here. This is an example that I used, I think, 2 months ago, where there's two ways, for instance, to implement a certain use case. This is a use case where the order lines of high-risk orders that are still open needed to be decreased in the discount percentage. You can do that with a single set-based update, or you can do that with multiple SQL statements where you first look, is this a high-risk order? Then you fetch all the order lines, and for each open order line, you reduce the discount percentage on that order line. So here I'm sending multiple SQL statements to the database. Here I have a single SQL statement taking care of that. Another way to look at this is here the business logic, which you could see as the blue bits here, live outside SQL. And here all the business logic is embedded inside the specification of this single update statement. So you move business logic into the SQL statement, at the same time affect multiple rows at the same time, or you move all this business logic outside of the SQL statement, and what remains is primitive row by row SQL to interact towards the database. Now, visualizing that, so here we have the UI tier, here we have the application server tier. If I have all the business logic outside SQL, I'm sending all these many SQL statements, and that's what we mean by a chatty behavior of the application server towards the database. Many round trips between these two servers, or I have one update statement, which at the moment here I'm sending over to the SQL engine inside the database server. Of course, the update statement could have been embedded inside the stored procedure also, and you would then just call the stored procedure to get this use case done. Now, there are many current trends since we've seen the dawn of this layered software architecture. The past 5, 6, or 7 years, we see a lot of logic being moved towards the JavaScript engine inside the browser. There are things going on in the microservices architecture, where we, instead of build monoliths, introduce many small APIs, microservices, and attach these together to get our work done. There's this serverless move going on. And actually very lately there's this thing going on where we move away from REST and maybe start using GraphQL, where we again instead of having multiple REST calls to get our stuff done, have something more sophisticated use of a chatty behavior from the application server towards the database server. But all these trends in general, they aren't changing the fundamentals, being we still see primitive use of SQL, we still see a chatty behavior towards SQL, and we still see this third thing going on. Now, this is the preludes that I wanted to get away with, making sure that layered architectures, we know what we mean by that, and in general, what are the implications in the performance dimension for those. Let's now move on to some database performance core principles. And this is actually stuff that you might have had when you were going through your formal education. But let's touch on these anyway and make sure we are all aware of them. Now, the thing to realize is that the Oracle database is a process architecture. And the fact that the Oracle database is a process architecture where for each session there is a foreground process that services database calls, this fact has implications that I want to talk about. The second thing is response time. What's important with respect to response time, and how is response time, what are the different components inside response time? I'll talk about these 2 points and at the same time touch on layered software architectures and SmartDB approach as we go along. Now, the fact that Oracle database is a process architecture means that for a process architecture to perform efficiently, you need a couple of things. You need, for a process, once it has work to do, to get on the CPU as soon as possible. I'll talk about that. But also, once a process is finally on CPU, to have as much work as possible so that it can stay on CPU, because that's how process architectures operate efficiently, and I'll talk about that. And the third thing is a process needs to experience as few involuntary context switches as possible. Now, this all seems a little bit technical, but I'll explain what I mean by these. So first, a process needs to get on CPU. So here I have my little core on my database server. It's idle, it's doing nothing. And here's my database foreground process, also idle currently, not doing anything. And at some point, a database call comes in via the application server. An application thread has acquired a connection, and it issues a database call across that connection. So my foreground process now needs to wake up operating system-wise. What that means is the OS scheduler needs to get this process on CPU. It needs to move from an idle state to a busy state on CPU so that it can start work on the database call that has just arrived at the database server. Now, here's what you need to realize. Let's suppose the CPU wasn't currently idle, but it was 50% busy because other things were going on the database server. Then there's a chance of getting scheduled immediately of 1 in 2. If the CPU is 50% busy, the chance of getting scheduled immediately is 1 in 2. And this rapidly decreases as your CPU becomes more busy on the database server. If your CPU is 80% busy, then the chance of getting scheduled immediately is 1 in 5. 90%, the chance of getting scheduled immediately is 1 in 10. Yeah? If you don't get scheduled immediately, what happens then? Well, your process can't start working on the database call it has received. It has to spend some time on the operating system run queue. Now, and the variance of the user response time, and I'll have a graph for this on the next slide, becomes noticeable at about 60-65% busy CPU utilization on a database server. This is not something new. This has been observed in production and laboratory conditions for many years. This is basically a bit of standard queuing theory. The formula that plays a role here is this one. The response time of a request that needs to be serviced on a resource that has a certain utilization percentage equals the service time once it is on the resource divided by 1 minus u. Yeah? So let's say utilization is 0%, you get scheduled immediately, then response time equals service time. 0%, let's say response time, service time normally is 1 second, then your response time is the 1 second because you get scheduled immediately on the resource, in this case the database core. But as busy rate of these resources increase, you get this curve here, and you definitely don't want to be here. You don't want to be beyond, let's say, 65, 70%, because that's when the variance of getting scheduled, the wait time that you experience before you get scheduled, really becomes noticeable. And this curve actually depends on what's the arrival rate of your requests. What I have here is random arrival rate, but if you have different kinds of arrival rates, this curve may be more aggressive or maybe a little bit less aggressive. But normally around 65, 70%, you really do not want to go beyond that on your database core busy rates. So that's one thing. Yeah, you need to get on the CPU because it's a process architecture. You need to get on the CPU, and you have to deal with this phenomenon here. And whatever is between response time minus service time, again, that's the queue time that you're waiting for this resource, the CPU, to become available. Now, the other thing that I said is once you are on CPU, it's good to stay on CPU and do as much work as possible. I'm visualizing this here, where I have a foreground process that's servicing 10 row-by-row SQL statements, and let's say a foreground process that's servicing a single array-based SQL statement. So instead of, let's say, 10 single row insert statements, I do an array-based insert of 10 rows, which is one call. Yeah, so instead of going off and on the CPU, I stay on the CPU a little, I do my work, but on the left side, I'm still going on and off the CPU. Why am I going off the CPU? Because I'm going out of the operating system. I'm going out of the operating system back to the application server for it to generate the next insert statement so that I get scheduled again, etc. Yeah, so I have 10 voluntary sleeps going on here for this operating system process. And it needs to get scheduled 10 times on CPU, where I have this R equals S divided by 1 minus U going on. But I also have, and this is the point that I most notably want to make here, is I have 10 CPU context switches going on. Because in between, when my foreground process voluntarily goes to sleep, very likely something else quickly gets scheduled on this core by the operating system scheduler. What that means is that all my code and data caches on the chip, on the level 1, level 2, level 3 caches disappear. And the next time I need to get on the chip, they need to be refreshed again. And that's all part of what's called a context switch. Now, you may say, well, what's a context switch? That's not, should I care about a context switch? Well, yes, you should care about a context switch. Here's a little visual where we have on the axis here various kinds of things that a CPU core can do. Things from simple register to register, add, ORs, or logical ANDs and stuff like that. Branches, ifs, level 1 read, level 2 read. And what you see here is the number of clock ticks it takes to do these operations. So this is 1 clock tick. This is 10 clock ticks, 100 clock ticks. There's a logarithmic scale going on here. And when we do work in the Oracle kernel, processing SQL or PL SQL, these are the kinds of operations that are being executed on the core. Lots of these kinds of operations. Now, what you see here is that, actually, can you see this? I'm having this thing blocking me again. So is that a thread context switch is the most expensive operation that a core can make.
Yes, Toon, we can see it all.
Okay. So this is almost 10,000, 100,000, maybe even 1 million clock ticks to get a thread context switch, including all the cache invalidation and reloads to get that done. So you want to not hit thread context switches frequently because they cost an enormous amount of clock ticks on your CPU. And while this is going on, while a thread context switch is going on, well, that core is not doing anything else. It's working on a thread context switch. Now, and imagine 100,000 clock ticks. How much of these things you could have done had you prevented the thread context switch? Yeah, this is really a major thing going on practically on almost every database server nowadays that runs layered software architectures. So not only are you experiencing these 10 context switches, but since you're going back to the application server and back into the database server, you also have 10 operating system entries and exits. You have to traverse drivers on the network card, layers in the operating system with regards to TCP/IP before we are actually at the socket that this process is listening at, and the OS scheduler can determine, okay, this socket has a new message. What's the process listening to this socket? Oh, I need to start scheduling this process. Yeah. So there's a lot of overhead just in the operating system software, not just on context switch microcode that runs on the course itself. But then also we are entering and exiting the Oracle code 10 times. When you get a SQLnet message to the foreground process, the Oracle foreground process, it's not immediately delivered at the SQL engine or the PL SQL engine. It has to go down and into the Oracle kernel, and it has to traverse 10, 20 software layers before you end up at the SQL or the PL SQL engine. And that's all overhead also for every call. And going back up again is the overhead, going back all the way to the other side. I talked about this earlier. So it's getting scheduled 10 times, 10 context switches, 10 operating system code paths need to be run, 10 Oracle code knock-on code paths need to run before the actual SQL can get run. And this all adds up and becomes a significant amount of the CPU being burned on the database server. The third thing that I want to talk about is, I talked about just now this voluntary context switch that I mentioned here. Voluntary context switch is the process are done working and you voluntarily go off the CPU. But we also have this thing called involuntary context switches. And that's happening when you are on the CPU, you still have work to do, but the OS scheduler decides to get you off CPU and allow another process that wants to do work on CPU. Yeah, so you get this kind of thing going on where many processes are wanting to work on a database call, but the number of processes exceeds the number of available cores. Hence, all these processes start experiencing involuntary context switches, which again adds to overhead on the core because that's all thread context switches at the core level also. Yeah, so the OS scheduler deschedules processes while they still have more work to do. That's an involuntary context switch. Now, the impact of too many processes is not negligible either. Again, laboratory tests show curves like this, where, let's say I have a curve here where I have one process per core. So if I have 4 cores, I have 4 processes. If I have 8 cores, I have 8 processes, and I can do a certain transaction rate with those. And as I increase the number of cores, I also increase the number of processes accordingly, and I can get pretty much linear scalability in that way. If I try to do the same thing with 10 processes, where each of those 10 processes constantly fights with the other 9 processes to get on the core, you see a gradual but sure degradation and deviation away from this linear curve. At some point, it just levels out, and if you go to 50 cores, at some point, it doesn't even get up high at all, and at some point starts dropping even. Yeah, so this overhead of all these involuntary context switches, they really start taking the majority of all the CPU cycles on your database server. So you do not want too many processes. Now, this now is a stepping stone for me to start talking 5 minutes about this third thing that I mentioned: long reservation times of connections from the connection pool. Because if you have long reservation times, that will give cause to many processes on the database server. Let me try and explain that quickly. So here I have a browser, and I have an application request, and I spend some time on the application server, and let's suppose I have to do 1, 2, 3, 4, 5 database calls before my use case is done, and I give control or result back to the front end at the end user side. At some point, probably here, we acquire a connection into the database. Yeah? The Java thread acquires a connection, and at some point here, it releases the connection into the database. So that's somewhere here we acquire the connection, somewhere here we release the connection. So if I now look at the breakdown during that time that I have the connection reserved, these are the points where I keep the foreground process busy, the red bits, because those were my 5 database calls. All the other bits is time spent in Java or on the network, back on the network, back to the application server, etc. Typically, a breakdown like this could be that the foreground process, that's the session process that I was talking about while talking about the OS scheduler and stuff like that, is only 10% busy. Because maybe it's spending 10 milliseconds here, but I only have 5 times 2 milliseconds doing SQL statement, and all the other time the foreground process is just waiting for the next database call to arrive and start working on it. Yeah, but if your foreground process is 10% busy, that would imply that you need 10 connections, 10 times 10%, to get one database CPU busy. If it's even worse, if your foreground process is just 5% busy, because this is longer or your network is longer or your database call are really fast because they are row by row processes, that means you need 20 times 5, 20 connections to get one database CPU fully busy. 2%, you need 50 connections. Yeah? In the real world, we often see this 1 or sub 1% busy rates of the foreground processes. Yeah, so and that means you need 100 connections to even be able to get one database core busy. So if you then have 16 cores and you have a software architecture that only keeps a database session 1% busy when it's using it, you already need 1600 connections to put load on the database server. Huh? And of course, I have to come back to my earlier comment. You never want to go to 100% CPU busy rates, but the order here is clear. You need 2 orders or maybe more orders of processes on the database server for your software architecture to be able to put load on the database server. This just follows from the way these layered software architectures keep foreground sessions not busy while they are using them. Now, what if instead of these 5 calls, you would bundle them all in one call? Yeah, then we would lose a whole lot of this reservation time, and we would go to a situation like this, where we spend some time on the application server going down JDBC layers, we cross the network, and then we do, for instance, a set-based update or a stored procedure call that has bundled SQL statements in them. Then we go back to the application server, upwards into JDBC, and we release the connection. We immediately get a much better busy rate of our foreground sessions. And we immediately enable our database to do useful work with less processes. In this particular case, 2 processes per core would be sufficient to load the database server with work. Yeah, so these are the 3 core principles that I wanted to talk about. It's a process architecture. You need to ensure that a process gets on CPU as soon as possible, which means you don't want 100% busy database servers. Equally, you don't want this at your application server either, by the way, because your Java threads need to wake up and get scheduled also. And once you are finally on CPU, the foreground process, please do as much work as possible and voluntarily release the core only as when you have done as much work as possible, and experience as few involuntary context switches as possible. Yeah, so as much work as possible means use array-based processing, set-based processing, or bundling of your database work in stored procedures. And involuntary context switches cap the number of foreground processes. Have an architecture that allows you to do the same load on your database server with less foreground processes, which simply implies make sure the busy rate during reservation of these foreground processes is high, is not 1%, but preferably 50 or over 50%. The inefficient use of resources we easily detect when we see an AWR. If we see an AWR, in the load profile, we can see how many calls does this database server receive every second. So here I have a case where we get 27 calls per second. Here I have a case where we have an enormous number of processes. It's actually been growing a lot during this 1 hour period, but it's a lot of foreground processes. And if we look at the operating system statistics here, we see an absurd number, high percentage of system CPU going on. This is all the work the operating system is doing, managing the run queue, making sure the thread context switches appear, getting all the involuntary context switches processed, etc. And in the user percentage, where we here see 32%, very likely because there is such a high call chatty behavior going on here, very likely a good 10% here might just be going in and out of the Oracle kernel, and only, let's say, 20% actually spending time inside the SQL server. Yeah, so here we have a system that, if we say, let's say that's 10%, more than half is not spent processing SQL. More than half is just spent on doing all the overhead because of this and this. The amount of inefficiency going on is that much that it allows us, when we rewrite this, to get these 1, 2, or sometimes 3 orders of magnitude improvement. Now, one final thing that I want to talk about, and that's response time. Efficient use of resources is what I've been talking about so far. The other thing is response time. And response time, there's actually 2 things going on. You want a good response time that's low enough that your users are happy with it, but you also want consistency of response time. That's equally more important. If your response time is not consistent, bad things happen. What do I mean by consistent response time? Here I have 2 scenarios. One scenario where I have the response time here on my horizontal axis and the number of times that a certain response time was experienced on the vertical axis. And what you would like to have is a single spike that has the most experiences are within, let's say, this is 2 milliseconds here in this example. And then we have a very short tail, meaning that very few times we experience a lot more than 2 milliseconds of response time. What you don't want is the blue curve, which is much more flat and has multiple humps and has a long tail, meaning you have a big variance in the response time that is being experienced. Now, how can we ensure that we have more likely the red curve than we have the blue curve? There's some theory behind this also. And again, it goes back to the fact that response time is built out of multiple components. Typically, you can break down the response time in a way like this. The total response time consists of time spent on various components. Very simple, this could be the application server, the network, the database server, but inside the application server or inside the network or inside the database server, there can be multiple components where you spend some time. Per component, spending time takes a number of milliseconds or microseconds, and you are on that component a certain number of times for a particular use case. So in total, you're spending X1 times C1 time on component A1, etc. for all the other components. Now, and what you may expect here is that there's a linear relation going on here. Linear in the sense that if I were to increase this C4, let's say that's currently 50, and I increased that to 100 because I changed my software code, and suddenly the use case now spends 100 times on component A4 taking X4 milliseconds every time. You might think that has a linear relation impact. So if I go from a call count from 40 to 80 or from 50 to 100, I see a linear increase in the sum of this column, in the total response time being experienced. But that is not true. The actual relation is not linear. The actual relation also slightly but slowly and ever so surely goes away from the linear curve. And what's even worse is the variance increases. And this all has to do with the fact that all the arrival times are random across all these components. So you start hitting all these slight wait times at certain points where you want to get serviced, but you can't get serviced. So what can you do to get more a red curve than the blue curve? Well, there's only one thing you can do, and that is make sure that the sum of all the call counts for your use case is as minimum as possible. Yeah? If you have a smaller number of call counts going on for a particular use case across all the components that add to your response time, you are more likely to get a single spike consistent response times. It's all theory we've learned back when we were at school and were taught these kinds of things, but we seem to have forgotten all about that. So for SmartDB and the core performance principles, this is where I now finish up and say, well, SmartDB ticks all these boxes. Yeah? SmartDB minimizes the call counts across components. You don't have the chatty behavior. You have a single call, preferably to get one thing done in your database. Using set-based SQL in conjunction with bundling of database work in stored procedure calls, you minimize these calls across components. SmartDB submits code to the database server instead of fetches data to the code in the application server. Yeah? So we submit code to the database server. We submit a set-based SQL statement that has a lot of business code in it to the database server so that we can keep the foreground busy a little bit more longer than just doing a single row SQL statement. And since we submit less times across a connection while we have a connection reservation, we get these better busy rate percentages of the foreground sessions. So we enable efficient use of connection pools, minimizing the number of required foreground processes on the database server. And this all contributes very heavily to the immense overhead that usually goes on, and getting rid of that overhead at the database server, getting rid of the inefficient use of the database CPU cores at the database server. And these are the root causes why we can get the 10x, the 100x, or even sometimes the 1000x speedups when we rebuild something and show it can be done differently without any performance or scalability issues. And that's basically what I would like to have said during this call. I say, Bryn, we open it up for some questions. They can be related to this deck or they can be different.
Yes.
I think we're open for all.
Good plan. I have a question, but I suppose protocol requires me to hold back until we've heard from the floor out there. Does anyone out there have a question ready? If so, make sure you unmute yourself and speak it out loud. And also please say who you are when you start to speak. I'm hearing a deafening silence so far. I don't want to jump in and hold back the reticent out there. Eric van Roon, you're normally a talkative guy. You have nothing to ask your countrymen?
I'm flabbergasted by all the math and the stuff, and so it's just sinking in. I'm trying to figure out the question.
Well, we of course have done our preparation properly here by making sure, I think, that we're recording this so you can replay it all at slow motion and go and make sure it sinks in. Well, I'm going to risk my question then, but if someone thinks they've got a better question, just cut across me. But my question is all about human factors, really, Toon. Because it seems to me that you've done several engagements, you refer to them frequently, where you were called in because the perception was that in some maybe unquantified way, performance was bad, and you get to the bottom of things and you attribute the badness to the effects you've been talking about today, and you show in a prototype alternative implementation what the performance potential is, what the current architecture where you're working leaves on the table, and you not only show just as a straight empirical result that by doing some magic behind the scenes things are, as you say, sometimes 1,000x better, but you can explain roughly, well, to use some word that we often hear, you can explain the physics of what caused the badness, attribute it to well-known, well-established and not particularly new principles, and show how the wielding of those same principles informs the design of the alternative implementation you met. So that was the background. Now comes the question. When you give that speech at the end of an engagement to the stakeholders, what is their reaction? I get the impression it's in some sense to dismiss what you've said and say, I don't believe it, I'm going to stick with what I've got. But that can't be right. So what's the range of responses you get?
I get the full range of responses. I get the response that you just mentioned.
Yes.
But I also get the response where they are very happily surprised and are willing and able to take on the new approach. But unfortunately, so I get all kinds of responses, but unfortunately the response most often received back is, well, that's all very nice and well, but we can't use this solution. And the reason for them not being able to use the solution is because they are how do you call it? They are locked into using the frameworks and the layered software architecture that's in place.
Is that a way of saying that the effort involved to correct the badness would involve essentially a total rewrite?
Yeah.
From the very scratch.
Yeah. It would require major development efforts to take on those set-based or array-based or less chatty kinds of solutions that give the speed up. And sometimes I'm not even involved with people who can make this decision, because there are architect teams that mandate a particular architecture which the developers need to adhere to, and again the solution that I show them can't be used then. But of course I only go down that path if they are willing to look at the solution. So if at the beginning of a project I know they are not even willing to go into that area or wanting to see these kinds of solutions, yeah, by now I don't even start working on it like that. I just say, well, then I cannot help you.
It's a depressing, but I suppose completely accurate characterization of the world out there. Are there any cases where at least you've been able to convince them of the unassailable logic of what this presentation explained, and hear that they will, in recognition of the fact that they're too deeply in the present thing, go about things differently in the next project that one presumes, already have roughly in mind, in prospect?
Yes. Those kinds of reactions are also there, where they appreciate the solutions, directions, and the different way of solving the problem that they have, and but then they just park it and reserve it for future releases, and the turnaround of the releases is often multi-years. So I may hear back from them in 2 or 3 years from now.
Yeah. Does anyone else out there have experience of either? Well, I know the question to this. Yeah, sorry. The answer to this part of the question is yes, but I'll put the question anyway. Does anyone out there have experience either of A or B? A is a bad system that has all the features that Toon described that lead to the unacceptably long, or I should say longer than you ought to get response times with the big variability? And does anyone at the other end of the spectrum have experience of something which is pretty much textbook SmartDB? It's really the A part, the bad system, bad in the ways that Toon explained, that would be more interesting, because I'm interested to hear how you have ended up in that situation and what chance you might have to influence changing it. So anyone out there would like to talk about a use case A? There's one inevitable conclusion from the silence then, and that is everyone on this call, well, there's two, obviously. One is that everyone on the call is desperately shy, of fair number out there, 20 or so, is it? And the other is that every one of you is lucky enough to be working in a full-on SmartDB style. I could easily put this to the test, but I know that is Oren still there? Seems to have...
Yes, I'm here.
Yes! Well, I don't know if everyone on the call knows your story, Oren, but why don't you give us a brief summary of your story? Because I would claim, and you tell me if I'm fair in saying this, that your implementation at MoveIt is full-on textbook SmartDB. Would you agree with that characterization?
Yes, pretty much. I don't know if I tick all the boxes, but it is pretty much SmartDB. And actually, this is because the experience of 25 years developing Oracle-based systems, and I have seen type A, and I have seen type B, and the conclusion is that SmartDB works. And I had the privilege to start at MoveIt in the first day, and it was about 7 years ago. And we started right from the beginning using the principles of what you call today SmartDB. And we are very happy with it, and it proves itself to be a successful methodology. Now, I can say a bit about places that I've seen what you call type A.
Yes, please do. I also call that no PL SQL, for want of a better term.
Yes, definitely. And one of these cases, there were several where I visited as an outside consultant. And usually they call me when things don't work well, you know. And I think the best way to convince...
Yeah.
Sorry, Bryn?
I was just going to say, when you say don't work well, is it specifically and exactly about performance in its various different ways of characterizing performance? Or is it sometimes, let's say, bad data or hard to maintain, things of that sort?
It's usually performance. Mm-hmm. Because when things perform badly, then people convinced that they have a problem. They claim that the problem is in the database, usually. And the best way to show them otherwise is to take the thing that currently doesn't work well and just convert it to a PL SQL procedure, for example. And these are cases that it's really easy to show people that the database works very well if you put the logic in the database. And I have experienced places like this, where they started with no PL/SQL and they didn't want to hear about PL/SQL. And then I added one procedure to solve one problem, and then another procedure, and then packages, and they wanted PL/SQL because it changed the game in a really big factor.
Yeah,
and I find it much more convincing than telling people, Toon does, you do a great work explaining all the theory.
Mm-hmm.
But when people suffer,
when they
so who's speaking now?
So when the people say the problem is in the database, or when they say the problem is in the database, theoretically they are true. The problem is the database. But the problem is the database because of all the overhead that you let the database spend work on. But the problem isn't really, the root cause isn't the database. The root cause is the architecture that makes so inefficient use of the database server. Had, for instance, I'm unaware of the size of your production environment, Orn, but very likely, had you not chosen a smart database approach, but had you chosen an approach where all the logic had lived outside on application server, and you would have had a massively chatty application architecture, I estimate that your current production server, database server farm would have to be 3, 4, 5, maybe 10 times more than you currently have running all your services on.
Interesting.
Yeah, right.
I wonder if I should cut in and read out a question. It's from someone called Sherv. Is this the Shervin I know from the days of MoneyGram by any chance? Yes, it is. Okay. Too shy to speak. I'll read out the question then. Could you please talk about the impact of this approach? In other words, I'm sure he means the SmartDB approach, on database license and maybe total cost of ownership. Would it require more database cores or less, or does it just depend? And he's focusing here on the fact that the database license is more expensive than an application server license.
Okay,
yes, this is one right for you, Toon.
There's a very simple answer to this very good question. SmartDB requires less database cores. I've seen it happen time and time again. SmartDB requires less database cores. Why? Because you make much more efficient use of those database cores. If you move away from SmartDB, your database cores will start spending a lot of time on a lot of their clock ticks on things that have nothing to do with processing SQL or processing PL/SQL, if you were to use PL/SQL at all. So, and the fact that they start using a lot of the clock ticks on all this other stuff that I've been talking about in the presentation of today means that you need more database cores if you move the business logic out of the database. And moving the business logic in a smart way back into the database, preferably via set-based SQL, otherwise via bundling your SQL work in stored procedures, gets rid of the inefficient use of the database cores. Thereby, these database cores, they suddenly have many, many more clock ticks available to do useful work. And this is more than ample of clock ticks that become available to start doing the business logic on the database server. That's the general experience that we see out there.
I believe that it's our friend Pete de Visser. Are you Pete? Are you PDVBV by any chance?
Yes, he is.
Yes, he is. Right. Yes. Well, he says, though he's too shy to say it out loud, that he can confirm that this SmartDB approach needs less database hardware. He's completely convinced of that. When you say, Pete, that you're completely convinced, is it P or Q? Because A and B are used up. P is because of the overwhelming, unassailable logic that Toon just presented in the mathematical sense, or Q, you've actually been able to do a A-B comparison in your real work? Which of those is it? Empirical outcome or theoretical conviction? Seen it in practice, says Pete. Well, there we have it. I've got a question for you, Oren. We've still got 5 minutes left. You said that you were able, having in some presumably completely standalone prototype, I'm guessing, you were able to introduce the use of PL/SQL incrementally on each successive use case, which presumably at the moment you did it was the worst among them all. How were you able to do that in the context of what we hear about these frameworks that are so draconian in the discipline they the discipline they impose on developers, that you can't get at anything by hand? What kind of client-side environment were you able to introduce using PL/SQL gradually into? Did that question make sense, Oren?
I'm not sure I got it.
Yes. We often hear the point, and Toon made it, that when he explains all the principles, all the physics that he just did today, some of the suffering customers he's worked with throw up their hands in desperation, say, loosely speaking, that's all very well, but we're just too stuck too deeply in our present scheme to do anything. But you mentioned that you were able to introduce the use of PL/SQL on a use case by use case basis. So I'm asking, what sort of client-side architecture allowed you to do that, where we so often hear that the generation of SQL is so firmly embedded in the paradigm that you just can't step outside of it? Do you see what I mean now?
Yes, well, there was, as far as I remember, one environment was .NET and another one used JDBC. And do you mean bureaucracy-wise?
No, I meant more to do with the practical constraints on how you develop things that a framework that was in use impose. So was the starting point in your case basically handwritten, row by row SQL in ordinary code written by an ordinary developer that could be relatively easily rewritten to make a single top-level call to a PL/SQL procedure? Was it that kind of scheme?
The worst cases were when Hibernate was used, and the equivalent for .NET, I don't remember its name, but still, you still can call a stored procedure from these frameworks.
Yes, yes. So the question to you, Toon, given Oren's experience, that if you've got a will, you can, on a case-by-case basis, improve the worst use cases by incremental introduction of PL/SQL. Have you found just opposition to even that in some of the projects you've done?
Yeah. It's really, it depends on the project. It's on a project by project basis. If I hear Oren say it was .NET, then I can imagine gradually. I can imagine allowing SQL stored procedures, because it's basically, well, I think it's not really a layered architecture. If you just have JDBC on the application side and not all the frameworks, again, I can imagine stored procedures being more easily added to the architecture than in cases where we have many frameworks. That would make it really difficult to have a separate channel alongside the frameworks to also have SQL going back and forth between the application and the database.
Right. So we're almost out of time now, but there's a certain amount coming in on the chat, which makes it hard deal with everything. I'm afraid it's hard
well,
to.
there's a question from Sanjeev. How do you deal with new age thinking where a database is treated just as a container to store data rather than doing proper data modeling complying to RDBMS? Well, how do I deal with it? We deal with it, for instance, by doing these office hours, by educating and showing how the new age thinking, again, which I think was born out of developer productivity and abstracting all the mundane work away for developers, how this thinking gives rise to hugely inefficient use of the resources available to you, and how a different architecture, which would require different developer skills, enables you to make a hugely efficient use of all the available resources. That's so the way we deal with it is by just showing them and doing these office hours, presenting on conferences and talking about this and trying to get the message out there. But what I know, Bryn and I will not change the world. Yeah, but but there's a drive in both of us, Bryn, that we just keep on bringing this message.
Exactly. When you know what's right, it's hard to keep quiet. Maybe I'll just read out a couple of comments and then we should stop because we are a minute over. We have one from Claudio, whom I don't think I know, who said in his or her words, his I assume, more or less what Toon just said. I'm paraphrasing. It was that the only approach we have is by explaining the physics time and time and time again. And our friend Pete says patience is what you need. And now we have one from Judith who says that this database as a bit bucket, to use a different expression than she did, is the approach used by products whose strongest point is to claim database vendor independence. And well, we've heard that so much. She says that everyone who's got a deep understanding of Oracle and how it works is surely convinced that this, what I have been calling no PL SQL approach, what she calls ThinDB, is the wrong one. And yet another point which depresses me to tears every time I hear it from Sanjeev, he says that the bigger problem here is getting good PL SQL developers into the market. I would actually prefer to say that differently. I think the problem is rather that whoever is writing up a job description or trying to find staff is just explaining what they want in the wrong way. If only they said they wanted people who had a solid background in some of the underlying principles of computer science, these things to do with queuing and the like, as Toon explained today, and someone who is ready to learn and someone who is interested in writing highly performant applications, then they could attract people, because after all, PL SQL is not rocket science to learn. And as so many people have said long before I said it, the problem, the challenge when you write PL SQL is not the PL SQL, it's the SQL you write out of it. And really the challenge then it all boils down to is whether you're going to generate your SQL with all the things that it implies, or learn what it really can do for you and simply write it. Well, I think now that everyone is saying similar things, and we've, in a sense, I'm sad to say this, we've been preaching absolutely to the choir as far as I can see. We have a faithful crowd out there. So I can only hope now, as we wind up, and I'll let Toon have the last word, that while you all out there were already convinced before we started talking, you may have found, especially in today's deck, some arguments in very terse and reusable form that you can then try out on your own naysayers who are trying to argue for the way of doing things that we all know to be bad. Right, Toon, you can close the session.
So one thought that I had going over these comments of the past 5 minutes is, wouldn't it be nice that if the senior developers that were successful in the 90s and maybe a bit in the new millennium gradually start turning into development managers, and that these new development managers start hiring the right people and start bringing back the SmartDB approach in order to deliver more scalable applications, that have a better performance and that are easier to maintain, and all the other benefits that we've talked about the past year. Wouldn't that be nice? But let's close with that.
Right then, thank you all for attending, and thank you, Toon, for doing the groundwork to prepare your slides for today. So see you all in 4 weeks, the 3rd Tuesday of March it would be, I think. Bye for now.
Yep. Okay. Bye-bye.